All right, I am back in my classroom after construction, which is very exciting for me, and this is the second part of the Scalar Product video that I want to make. If we hear loud banging, that's because they're now doing construction on the room next to mine. So who knows if it'll show up on the video. But, okay, so we made it through talking about what the scalar product does, how to find the scalar product. Then we started talking about the law of cosine. Okay, so we use the law of cosine here. Well, now they're wanting us to write the law of cosine, so to come back to this, but put it all in terms of these vectors. So write them all in terms of just the components of the vector. So what we have is that cosine of c, I lied, cosine of theta, whatever, is equal to, well, the magnitude of vector A. Let's see, so vector A is just this A, so the magnitude, let's write that somewhere. The magnitude of A would be equal to the square root of A1 squared plus A2 squared plus A3 squared. Maybe I should put these in parentheses, but that's going to give us a whole lot of parentheses as we go. The magnitude of B is going to be equal to the square root of b1 squared plus b, that notation just bothers me, b2 squared, and we'll see how I can handle that, plus b3 squared. So it's the square root of those terms squared. But what we're about to do is we're about to square these things, okay? So this, the magnitude of a squared becomes a1 squared plus a2 squared plus a3 squared. And then the magnitude of b, so this first part right here is that, okay? Then the next part becomes b1 squared plus b2 squared plus b3 squared. Okay, and now what we need to do is we need to subtract this guy squared. I've run out of space. Okay, let's see. Everything is going to get divided by 2 times the magnitude of a1 squared plus plus it's almost spring break. I'm so excited, y'all, but I'm a little distracted. And then times the square root of the b1 squared plus b2 squared plus b3 squared. Okay, well, my handwriting's terrible. Minus, okay, so we need to do the magnitude of c squared. It needs to fit into that spot. Let me get more paper, and I'm going to turn it the other direction. Okay, so what happens here with this, so this, think of this as scratch work. Where'd it go? Okay, the magnitude of c needs to get squared, so that'll cancel out that square root. So now we need to FOIL out each of these, and so this becomes, okay, can you see what I'm doing? Well, maybe, here we go. The magnitude of c squared ends up equaling, the square root's gone, and so now I have b1 minus a1 squared. Well, okay, so here, b1 minus a1 squared, then it's b2 minus a2 squared, and then it's plus b3 minus a3 squared. Okay, luckily we know how to square those guys, so yeah, that's exactly, I took out the square root. So now this is equal to b1 squared minus 2a1b1. My brain just stopped. Okay, plus a1 squared. And then I keep doing that basic idea. Okay, so then this becomes plus b2 squared minus 2a2b2. I'm putting them in alphabetical order just for the fun of it. Plus a2 squared plus b3 squared minus 2a3b3, oh, I ran out of space, plus a3 squared. Okay, so that's what happens when we expand it. So now when I look back at these two components, what I'm about to do is I'm going to take all of this and subtract away all of this. Okay, so this, the magnitude of c squared is equal to all of these terms. Well, notice, for the sake of saving space, I'm going to just kind of show you what happens. We subtract all of this. Okay, so that means that this a1 squared cancels with this a1 squared because we're about to subtract them. This a2 cancels with this a2 squared. This a2 squared cancels with this a2 squared. A3 squared cancels with this one right here. The b1 squared cancels with the b1 squared here because I'm subtracting away all of this mess. B2 cancels here, b3 cancels here, and then I have a negative that is going to change the signs of these three things right here. So what's about to happen is that I end up getting that cosine of theta is equal to, well, it's these right here without the negative. So it becomes a 2a1b1 plus a 2a2b2 plus a 2a3b3 because everything here canceled when I expanded this, and then I distribute the negative through, and those terms became positive. So it's divided by, and actually, I forgot, I don't need to expand this out because I'd forgotten the formula. So this is 2 times the magnitude of A times the magnitude of B. Well, notice I can factor out a 2 from on top, and this gives me cosine of theta, and that 2 on top will cancel with the 2 on bottom. This is equal to A1B1 plus A2B2 plus A3B3 all over the magnitude of A times the magnitude of B. Well, what do we know about this? A1 times B1 plus A2 times B2 times A3 times B3. Look, that is what we call the scalar product. Okay, so it's right there. And this, ladies and gentlemen, is why we care. I mean, it's fun to take the scalar product, I mean, if that's what you're into, but there's a reason that we care, and that's because the cosine of an angle between two vectors ends up becoming the dot product of the vectors divided by the magnitude of the first vector times the magnitude of the second vector. And so this is a lovely formula, and this is really and truly why we actually care about taking the scalar product. So in summary, what I did, I used the law of cosine, expanded this out. This wouldn't quite count as a formal proof because you'd kind of need to see all this expanded, but it didn't fit on my paper, and I don't know that they're going to ask you for a formal proof. But this is what happens. So all of these terms here canceled with some of the terms here, leaving me with this. The 2 factored out, the 2 canceled out, and this is the dot product right here. Okay, so let's do an example. Yeah, here we go. Well, we'll save this example for the next video. Come back for more. Okay, goodbye.